Hi, my name is Susanna Gordon, and this is my Lab 4 report for Physics 2212 with Professor Junker. So, let's get into it. So basically the background for this lab was to get us more familiar with circuits, since that is what we're now currently covering in our physics class, and we're using an online simulator to learn more about that, current, resistors, voltage, and capacitors, and also becoming familiar with voltmeters, which measures potential difference, and ammeters, which measure current, and also become more familiar with RC circuits, which is a really tricky concept in circuits, which is basically a resistance capacitor circuit that's time dependent for both current and voltage. So the first steps of this lab, we're looking at ammeters, and ammeters you can put directly into your circuit, and it measures the current. And then in these you can see that the current in both places is 0.02 because they are both in series, so there is no node rule. So the current there should be constant, and even if you switch the current or switch the ammeter, which one's positive, which one's negative, or the position of it, it's still the same current. So this is just getting used to that. It doesn't matter which way you put it, it's going to measure the same thing as long as it's in series. With voltmeters, however, when you're using it to complete the circuit, in this case it was -3. And this one really does depend on which end is on which part of the circuit. So if it's going from a higher potential difference to a lower, it's going to be negative. But if it's the other way, it will be positive. And you can see here it's going to -3. But in other cases, it could be +3. So that explains a lot about that. And in terms of and with voltmeters too, they're different than ammeters because they really just do depend on the location. For potential difference, then, I measured the location of voltage at each of these different locations, and I finished the graph. So at A and B, it gains 1.5 volts each, which is a total of 3, which is why it's 3 there. But then across the wire itself, there is supposed to be no potential difference. Going from C to D, however, you have a difference of -0.96, and then from E to F you have a difference of -2.04, and this is because going across the resistor you're going to lose current, but there's none going across the ammeter. And then in this case, when you put it in parallel, you get a different current, and this is because when it's in parallel, it's going to be traveling across the path of least resistance in this case, and since it's not going to lose any voltage going across the 0.06, it's going to want to go across that way in that path. And with the node rule, that makes a lot of sense. And through this lab too, we are using Ohm's law, which is V equals IR. So I calculated the resistance across the 47 ohm and 100 ohm wire to see what I'd get. And based off of the values we got, the 47 ohm is about 48 ohms according to these measurements, which makes sense, and there's slight error due to approximation of values. Same thing with the 100 one. Across the wire and ammeter though, there is 0 ohms for the resistance there because there was no voltage difference. RC circuits, though, however, are time dependent. So in this case, we charge and discharge a 10 ohm and a 20 ohm light bulb. So to charge and discharge a 10 ohm, I got to be about 6 seconds, and then charge and discharge a 20 ohm, I got to be about 10 seconds. But then we were asked to calculate it for a 30 ohm light bulb. So I use this equation given to us, where it's natural log delta V over delta VO is equal to -T over RC. So basically, I pulled out I used and collected some data, and for example, I collected it at 30 seconds, I got the voltage was -6 volts. So plugging it into the equation with that time and that voltage difference, I was able to approximate what RC should be, which is about 5.87. It's supposed to be about 6 because the resistance, 30 times 200 millifarads, which is 0.2, it's going to be about 6. So that makes a lot of sense in terms of those calculations. Then final questions, if we're doing this in real life and use an actual ammeter, what would the difference be? In an actual ammeter, you're going to have resistance in there. So it will be less current than there actually is, because some of it will be, you will be having some dropout because of the resistance in the ammeter, and this is a perfect ammeter, so there's going to be no resistance. The same thing with the wires. In an actual thing, the wires have resistance in them. It's very small, but it is still there, so your numbers are going to be different. And same thing with a real battery, you're going to have some resistance in the battery too. So if you're charging it with a capacitor with no resistor, they're still going to act like there's a resistor in the circuit just because there is a small resistance in the battery. So this will cause it to be also different values, and it really just really depends on the materials you're using, because also over time the materials will wear out and they won't be as brand new, while in like a virtual experiment it's always going to be exact based off of measurements. I know that was really quick, but I answered everything I needed to, so I hope you learned something. Okay, bye.